In the last video, we spent a good bit of time going over this. Standard cell potential is the standard reduction potential of the reduction process, which is just another way of saying the cathode, minus the standard reduction potential of the oxidation process, which is the anode. In this video, we're going to talk about how this relates to Gibbs free energy and the equilibrium constant. So, for this equation, any combination of half cells that yields a positive E, a positive cell potential, is going to be spontaneous, and any combination that gives a negative value is non-spontaneous. And this should remind you of Gibbs free energy, except flipped the opposite way. Because remember, Gibbs free energy, negative values were spontaneous, and positive values were non-spontaneous. Well, it turns out there is actually a relationship between Gibbs free energy and the cell potential. And we have two different equations here because this one is at non-standard conditions, and the one down below is at standard conditions. But they're essentially the same equation. It's just one is standard and one is not. And so the Gibbs free energy for a chemical reaction is equal to negative N, N being the number of moles of electrons that are being transferred, times F, which is a constant, Faraday's constant, which is given right here, 96,485 coulombs per mole, or joule volts per mole, or joules per volt mole, I should say, times the standard cell potential, or just the non-standard, depending on which one you're looking at. And so this is actually a pretty useful equation for going back and forth between the Gibbs free energy of a chemical reaction and the standard cell potential or non-standard cell potential, depending on what you're looking at. So with that in mind, let's go ahead and use that. So we have an example problem here where we are asked to use the tabulated electrode potentials to calculate the standard Gibbs free energy for this reaction, and to figure out if it is spontaneous. So we have our two half reactions happening here. We have I2 going to 2I minus, and we have 2Br minus going to Br2. So just from looking at the oxidation numbers here, this is going from 0 to -1, so that is a reduction. So this is our cathode. This is going from -1 to 0. That is an increase in the oxidation number, which means it is being oxidized, and so it is the anode. So let's go back and find the two standard reduction potentials for these things. Oh, and I guess I should, real quick before we do that, the reason why I'm getting these, again, because we're using this equation, we need these to find this. Since we are working under standard conditions right now, we're going to use this down here. So we need those numbers to get E, and then we'll also use the table to find N here in just a second. But for now, we're going to just find E, because we know we need that. So if we go back, I2 and Br2 should be fairly close on the table. So there's I2 right here. Br2 is there. Actually, not as close as I thought they'd be, but oh, actually, that's the wrong one. Again, this is why you need to be careful when you're looking at these, because you can see that Br2 right there. It's weird. Why won't let me erase that? You can see the Br2 and think, oh, there it is, but this is. Oh no, wait, no, that is the right one. Yeah, going crazy. I need to record these a little earlier in the day, I guess. But my point still stands that you do need to still be careful when you're looking at these, because it is very easy to, for example, see iron 3+ here. And if you're looking for iron 3+ going to iron, you might just see the iron 3+ and say, oh, there it is. But it's not iron 3+ going to iron. This is iron 3+ going to iron 2+. So you do need to make sure that the reaction you're looking at is the correct one. So this is indeed the half reaction we want. So we have I2 and Br2. The Br2 is 1.09. I2 is 0.54. So 1.09, 0.54. Oops, too far. Too far. Okay. And now I've forgotten the numbers. I'm getting old. Getting old. Okay. Bromine 1.09. And iodine 0.54. 1.09, 0.54. 1.09, 0.54. Got it. Okay. So, to find that standard cell potential, we need cathode minus anode. So, this is going to be, since this is our cathode here, 0.54 volts minus 1.09 volts, which is going to leave us with negative 0.5-ish. Let me go ahead and plug that in here. Negative 0.55. Can't forget the negative there. Very important. All right, so actually I don't know why I'm putting a square around that. It's not the final answer, but it's leading us to the final answer. And it actually can tell us the answer to this last part here, which is no. As we can see, because we have a negative voltage there, but we'll see that again when we get to the Gibbs free energy in just a second. So now that we have this, we can plug that into here. So the standard Gibbs free energy, and this is from the previous slide here, is equal to negative NFE. And we just found E. F is a known, it's a constant. The only other thing we need is that N value, and the N value is the number of moles of electrons being transferred. And we are going to get that from the table as well. So if we go back to that standard reduction potential table, you'll notice this half reaction has 2 electrons being transferred, and so does this one. So what that tells us is that N for our process is 2. The oxidation is giving up 2 electrons, and the reduction is accepting those same 2 electrons. So N is not 4. We don't take the 2 from both and add them together. The N would be 2 in this case. If we're doing another reaction, like say perhaps we have one where one of our half reactions is giving up 2 electrons and the other one is giving up 3, N in that case is going to be 6. There's kind of an easy way of figuring this out, and there's a hard way of figuring this out. The hard way is to actually balance the entire process, to take the 2 half reactions, balance each individual half reaction, see how many electrons that you need to get the number of electrons to be equal from one to the other, and then that will be your value for N. The easier way is just to go ahead and figure out what's the smallest common denominator of these 2. Like, what's the smallest number I can get using only packets of 2 and packets of 3, which would be 6. That's the smallest number of electrons where those 2 can be equal. So this would be true for anything you come across. So if you had one where you had 2 electrons being transferred and the other half reaction had 4, then N would be 4. So you'd have this half reaction happening twice, this one happening only once, and so you would have a total of 4 electrons being transferred, 4 moles of electrons being transferred. All right, so I hope that makes sense. If not, we can talk about it when we get together. But for now, N is 2. So then, delta G, standard Gibbs free energy, is minus 2 times 485. Yes, 485. I remembered. 96485 although the units escape me now, coulombs per mole or joule volts. Joules per volt mole I think is actually going to work out better. Joules per volt mole times the voltage, which was negative 0.55 volts. And by the way, that actually should be a unit of moles there to cancel out those moles, because we have 2 moles of electrons being transferred. All right, definitely can't do that in my head. So, negative 2 minus 96,485 times negative 0.55 gives me the standard Gibbs free energy value for this electrochemical cell is, and I'm going to go ahead and convert this to kilojoules in my head, 106.1 kilojoules. Because the volts here cancel and the moles cancel. So for the reaction as written, it will be positive 106.1 kilojoules, which is quite non-spontaneous. Remember, negative delta G values are spontaneous. And so having 106 positive kilojoules, very non-spontaneous. All right, hope that one made sense. Just to carry that same thought process, this equation, the previous equation here, gives us a connection between the standard cell potential, or the non-standard cell potential, and Gibbs free energy. But if you remember from the previous chapter, we already know how to connect the Gibbs free energy value to the equilibrium constant. So because we know how to connect Gibbs free energy to the equilibrium constant, and we know how to connect Gibbs free energy to the standard cell potential, we can work out a connection here between the standard cell potential and the equilibrium constant as well. And so there's this big mess of equations here that, don't worry too much about this big mess here. This is just kind of showing how everything is interconnected. What I'm more concerned with you being able to use is an equation we'll see in just a second, but which is the Nernst equation, which I probably will save for the next video actually. But for now, let's go ahead and solve this equation. So this is telling us to use tabulated electrode potentials to calculate K for the oxidation of copper by hydrogen plus. So we have copper going to copper 2 plus, and we have H plus going to H2. I guess I should put a 2 there. So here we have something going from 0 to plus 2, so this is our anode, because we have oxidation occurring. Here we have a reduction in the oxidation number. It's going from plus 1 to 0, and so this will be our cathode. Don't even need to look at the table for this, because this is the standard hydrogen electrode, so it's going to be 0 volts. Copper I will need to look. I don't remember that one. So copper going to copper 2 plus. If I go back here, where is copper? Yeah, there it is. So copper solid, copper 2 plus, it is 0.34, positive 0.34. All right, so we found our 2 things on the table there, and both of them are transferring 2 electrons as well. So we are trying to find K. If we go back to that previous slide and look at some of the relationships here, I think the easiest one, because you can see there's a couple different ways we could do that here. This is essentially the same as these 2 here are essentially the same as each other, but I think doing this, using this equation, will be the easiest thing for us. Technically, we could use the standard cell potential, use that to find Gibbs free energy, and then plug that in here and solve for K. But we'll go ahead and use this equation, which will I haven't explained exactly yet where this equation comes from. I should probably rework this section of the slides, actually. But we will see where this comes from in the next video. It's related to the Nernst equation. But for now, we're just going to go ahead and stick it in there. So the standard cell potential is equal to 0.0592 volts divided by n times the log of k. So our standard cell potential is going to be negative 0.34 because we're going to have cathode minus anode. So it's going to be 0 minus 0.34, which is going to give us negative 0.34 volts, is equal to 0.0592. That's right. 0.0592 volts divided by n. And if you remember, n is the number of electrons being transferred. Both of these transfer 2 electrons, so n is just 2, times the log base 10 of k, the equilibrium constant. And by the way, this is only true at standard conditions, this equation, but we are working under standard conditions. So all we need to do now is solve. So we're going to have to do a little bit of log algebra here, but we're going to take the negative 0.34, multiply that by 2, divide by 0.0592. That's going to give us negative 11.48 is equal to the log base 10 of k. So if we raise 10 to both sides, that will get rid of the log and leave us with k is equal to 3.31 times 10 to the negative 12. Itty bitty. Very tiny k value. But we would expect the k value to be small because the cell voltage is negative, which means the reaction is non-spontaneous. In fact, the reverse reaction is spontaneous. So we're not making too many products with a non-spontaneous reaction. So this answer makes sense. Alright, in the next video we're going to talk about the last big topic of this chapter, which is the Nernst equation. I will see you all in that video.